Throughout this course, you're going to hear me say the following phrase: all of the electrons do the work. Why? Well, because electrons are lightweight, they're tiny, and they're highly mobile. Think of your cellular phone. Think of the battery that's in it that powers your cell phone, or the information being transmitted across the internet as you watch it. It all participates because of electrons. They have the least amount of mass of all subatomic particles that makes them quick and flexible. And it's the electrons that make it happen. So when I talk about electrons, when I talk about the idea of electron, there's a couple of ways I can represent an electron. One way is just an E with a negative symbol, and that is because the electron here, the lowercase e in the negative charge, tells you that it is an electron. In the future, we'll be using arrows for displaying information about how electrons move through a chemical reaction. Here we have a 1 electron process, a single hooked arrow. Here we have a 2 electron process. Now that 2 electron process is going to be more common in this course because those reactions are a little bit more frequent than the single electron reaction. Now, the other way to represent electrons is in the space that they occupy. What do I mean by that? Well, as we go through this idea of what electrons are and where they are and how they behave, we're going to encounter electron orbitals. Now, there are 3 types of relatively common electron orbitals that we will encounter in chemistry. But in organic chemistry, because we're simple, we want to make it as simple as possible. There are only 2 types of electron orbitals. The first one is an s orbital, and it stands for sphere. So you can think of an s orbital as a sphere. The next orbital we're going to talk about is a p orbital, or a pi orbital. And these are dumbbell shaped. And in organic chemistry, there's going to be a lot of these p orbitals and the interactions of p orbitals that we will encounter. Now, in the s orbital here, if we were to define the s orbital as a function, we would just say, okay, here's the whole thing. It is 1 shade. But for a p orbital, we're going to differentiate these 2 lobes. And so we would shade one of these lobes one color and leave the other one perhaps unshaded. Now, what that means is the shaded form of this lobe describes the spin of the orbital. Well, that doesn't mean anything. What does that mean? Well, let's think of a wave. Let's think of a wave on the ocean. It goes up and down. And if we're on this ocean, we wouldn't define this at sea level or this at sea level. We define somewhere in the middle as the average of that wave. And so here is a positive form of that wave, right? Here is the negative form of that wave. And for orbitals, we're going to represent it in the same way. It doesn't necessarily matter what shade we refer to as the orbital as long as we define it in that way. So if we have a shaded orbital and we say, oh, this is the positive form of the wave, we can refer to that as that. And then we have a negative form of that wave. And what happens in the middle between these 2 orbitals is a area where there is very little probability for the wave of the electron to transfer to the other side. And we're going to refer to this as a node. And that node basically says all the positive is on one side, all of the negative is on the other. And so there is no electron density in that line. Now there is a third type of orbital that we can invoke, that we will invoke in this course, but we're not going to talk about it too much. We'll talk about it during the workshop, and that is a d orbital. And there's many forms of the d orbital, but the most common way a d orbital looks is a cloverleaf. And the s orbital here has 0 nodes, the p orbital has 1 node. This molecule, or this orbital rather, has 2 nodes. Now, the electron density, because of electrons being a quantum mechanical behaving device, the node here, if we're saying that this is the positive, the electrons in this node can superposition themselves into this node. And they kind of go back and forth. But in this case, we have the negatives here and here. And so in quantum mechanics, again, we're not going to necessarily talk about this in any gory detail. But for quantum mechanics, these 2 nodes exist in the same, and these 2 nodes exist in the equal and opposite form. Now, just to be clear, we're not going to be dealing much with d orbitals. But it's good to be aware of how these things behave and why they behave. For the most part in this course, we're going to be focusing on s and p orbitals. But it is important to note the behavior of an s to the behavior of a p to the d orbital and beyond. There are f orbitals and g orbitals, and they get very complex and very complicated. We're just not going to cover that in this course. These orbitals and variations of these orbitals are going to be used to build molecules. And so it's important to know how these things work. And it's important to know why these things work. And it has to do with the behavior of the electron, because the electron does all the work.